Okay, let's get started. So the homework is due on Wednesday. Because sending emails is hard. But you should have everything now. And I dropped 5D dropped. And then the typo that I mentioned 3 lectures ago also got fixed, or 2 lectures ago. Right, so let's get back to talking about ODEs systems. But first, let's get back to talking about some more linear algebra. So suppose that you have an equation of the form ax equals b. And this is a matrix equation. So you could, for example, have something like, let's say, 3x plus y equals 5, and minus x plus 3y equals 1. So these are the types of linear equations that we saw in middle school, and you can solve them. But what we're going to do is we're going to translate this into a matrix. How we're going to write this is we're going to take the matrix 3, 1, -1, 3, which is a matrix with numbers in it, not variables. And we're going to apply this to the vector x, y. And the result should be the vector 5, 1. So this problem is nothing but the problem of solving a system of linear equations. Now, how do we go about solving this? Well, there are several ways that we can solve this. So we, if A is a square matrix, and only in this case, we can ask the question whether there's an inverse. And the property is that this has to be a two-sided inverse. So if you look at one-sided inverses only, then there are some non-square matrices that admit one-sided inverses. But we care about two-sided inverses. So this will only apply in the case of square matrix. And a square matrix is any matrix whose dimensions are n by n. Now, what happens if a matrix has an inverse? If A inverse exists, then Ax equals B. That implies that A inverse Ax equals A inverse B. And now the left-hand side is the identity times X. And the identity acts as a trivial map. So that tells us that X is A inverse B. So we're able to solve for X if we're able to solve for A inverse. But more generally, you can have non-square matrices, and you can have square matrices that aren't invertible. And by the way, the fact is A inverse exists for a square, if and only if the determinant of A is non-zero. And we spoke about the determinant before. And in this case, A is called non-singular. And it's singular otherwise, of course. However, there are other methods of solving it. AX equals B can also be solved by, well, let's say by hand or naively. Or using what we are going to call row elimination. I'm just going to abbreviate that. And so here I'll give you example of all three methods. So by hand, we have a system of equations from before. And so how would we solve this? Well, if we have this, then what we have is that y is equal to 5 minus 3x. And you did this in middle school. So negative x plus 3 times 5 minus 3x is equal to 1, which tells us that, so 15, and then we have minus 9x minus x, except for the fact that I copied the system down wrong, and I actually want to have a 2 here. So this gives me minus 6 minus 1, so minus 7x equals 1, which tells me that minus 7x equals minus 14, which tells me that x is 2, which tells me that y is 5 minus 2 times 2, which is 1. So x, y as a vector is the vector 2, 1. Okay, now by inversion. So I'm going to write this as a problem in matrix form, which I already did. Oh, that's something on my screen, not there. Okay, and so we know how to invert 2 by 2 matrices. We talked about what the process is. What you do is you swap the diagonal entries, you put a negative sign on the cross diagonal entries, and you divide by the determinants. So first we divide by the determinants, which is going to be 3 by 3 minus 1 by -1. So, sorry, except for the fact that I forgot that this is a 2. And then what we're going to do is we're going to swap the diagonal entries, and we're going to put a minus sign on the cross diagonal entries. So the denominator here is 6 plus 1, so it's 1/7, times 3 minus 1, 1, 2. And so what is this applied? So xy is the inverse matrix applied to the result that we want, 5, 1. And how matrix multiplication works again is that you do this times this to get the entry in these positions, which would just be this entry. So that becomes 1/7. And then here I have 3 times 1 minus 1. Sorry, yeah, minus 1 times 1. And here I have 5 times 1 plus 2 times 1. Except for the fact that that 1 is a 5. Sorry, 3 times 5 and 1 times 5. And then 1 and then 1. So 5 here, 1 here, 3, -1, 1, 2. And so what does this give me? Well, this gives me 15 minus 1, 14, divided by 7 is 2. 5 plus 2 is 7, divided by 7 is 1. So that's another way that we can solve this problem. Now, this fancy new method that I'm about to teach you is called by row elimination. And the point is that if I give you a 3x3 or a 4x4 matrix, then you're not going to be easily able to invert it unless you do a very boring Cramer's rule computation. And so for higher matrices, this is the way to go. And I'll do this example. So we started off with this example here. And so what we're going to do is we're going to write the system like this. We're going to write 2, -1, 1, 3. Then we're going to write a bar. And then we're going to write the result that we want, 5, 1. And now you're allowed to do 3 things. You are allowed to scale rows, multiply a row by a non-zero number. By scalar, non-zero scalar. You are allowed to interchange rows, swap rows. And you are allowed to subtract, add multiples of one row to another. And by the way, so what does this mean? What this means is that suppose that we have a solution xy to this. What this means is that's 2x plus 1 plus 1 y is equal to 5, and -1x plus 3y is equal to 1. And so basically what's going to happen is, well, if you have these two equations, then you're allowed to take this equation and you're allowed to multiply it by any non-zero number, and you're going to get the same system of equations, right? Similarly, if you take this equation and subtract or add some multiple of it to this equation, then you still have the same system. You can't multiply by zero, or else you'd actually be losing information, and then you lose a constraint, and then you get more solutions. So that's bad. And then if you take these two equations and you swap these two equations, then you still have the same system of equations. So all of these operations are justified. So let's see what we can do. What we're going to do is we're going to take this, and then I'm just going to copy it over again, except for the fact that it did not get that upper brackets. And we are going to put it here, and then we're going to begin reducing. And I usually reduce by writing curly arrows like this. So what I'm going to do is that I may as well add twice this to this. So I'm going to get a 0 here because I've added -2 here. Then I'm going to add 6 here. And then I'm going to add 2 here. And then I get the same row as before. Does everyone see how I went from here to here? Now I'm going to do 2 steps at once, and I'm going to actually 3 steps at once. I'm going to multiply this by -1 and swap it. So I'll get 1, -3, -1. And then I'll divide this by 7. And now I'm going to add a multiple 3 times this to this. So when I do that, I get 1 and then 0. And then I've added 3 here, so I get 2. And then I get 0, and then I get 1, and then I get 1. And so what does this tell me? Well, what this implies is that x equals 2 and y. That's not how you write it, 2, and y equals 1, because 1 times x plus 0 times y equals 2. So the vector xy is 2, 1. So that might have actually been just 4 short steps. This might actually be a shorter and more organized process than the other one, because you don't have to write x's and y's while you're doing it. You just have to do a bit of things, and then you get solutions. So here's another example. This time it's going to be a 3-dimensional example. So let's suppose that I have the matrix 3, why do I keep writing 3s when I want to write 2s? 2, 2, 2, 2, 0, -2, 1, -1, 1. Then what I'm going to do is I'm going to apply this to the vector x, y, z. And what I'm going to try and do is I'm going to try and get that to equal 0 to 6. So this is a 3-dimensional example, and this matrix can't be as easily inverted. There's no swap and put negative signs on the cross-diagonal term algorithm for inverting a 3x3 matrix. It's a bit more messy than that. You can give it an algorithm, but it's not as nice. So what we're going to do is we're going to set this up in the way that we did before. Then a bar here, and then 0, 2, and 6. Okay, so what am I going to do? Well, it looks like the same thing is that these look like very big, very multiples of 2, such multiple of 2. So I'm going to change those multiples of 2s to multiples of 1. And I'm getting some better numbers here by doing that. Okay, now let's take the first row and subtract it from the second row and the third row. So here I'm going to keep the first row. Then here I'm going to subtract 1, 1, 1. So I'm going to get 0, minus 1, minus 2, and then I'm subtracting a multiple of 0. So it's still just 1. And then here I get 0. And then here I get minus 2. And then here I get 0. And then here I get 6 again, because I haven't done anything. Okay, cool. So I guess right now, I mean, I can do this in lots of ways. I want to make this be diagonal. I guess I can just clean it up a bit. This is divisible by 2, so I may as well simplify it, and I'm also going to move it up here. And well, let's multiply this by -1, because why not? Okay, so I swapped these two, took a factor of 2 out of this, and then also multiplied this by -1. Now I'm going to take this and I'm going to add it to both of these. So when I add it, I get 1, then I get a 0 here, then I get a 1 here because nothing's changed. And then I get a 0. Wait, what do I get? No, I do not get a 0. I'm adding this row to this row, so that becomes a 3. Then this row stays the same. This row, so I get a 0 here, a 0 here. Then there's a 2 here. Then I've added 3 to this, so I get a positive 2 here. Then what I'm going to do is, okay, fine. I'm just going to write out an extra step because why not? Let's make this equation 0, 1, 0, -3. And let's make this equation 0, 0, 1, 1. So I multiplied that by 2. And now I'm going to take this and I'm going to subtract it from here. So I'm going to get 1, 0, 0, 0, 1, 0, 0, 0, 1, which is what I want on the left of this bar. And then here I've subtracted 1 from here and also 1 from here. So this is 2, -3, 1. And what that tells me is that my vector x, y, z is actually the vector 2, -3, 1. So there are sort of lots of ways that you can go about doing it. I did it in a way that's different from what's written in my notes. But the point is that you basically want to get more zeros, and then you eventually want to reduce it to a diagonal matrix. Any questions about that? Okay, let's do the next example. You can also use this to invert matrices. So in particular, this will let you invert sort of arbitrarily large matrices. So this is good because it's a process for inverting matrices. Let's actually find out what the inverse of a 2x2 matrix is. And so how we're going to do this is notice that if we have sort of a matrix and then we have a column vector and we're able to reduce that to the identity matrix, then the vector that goes here is by sort of what we were solving the linear system, right? So what this really is, it's A inverse V. That's the vector that you get here, right? Now, what if instead of putting a single vector here, we sort of put the identity matrix here, which can be given as a bunch of rows of elementary matrices. Then if we sort of kept multiple rows here and did all of the inversion, and we were able to reduce that to I, then what we'd actually get here is A inverse E1 through to A inverse En. And if you plug in sort of the elementary matrices of, if you plug in 1, 0, 0, 0 into a matrix, then you just get the first column. So this is the first column of A inverse. This is the last column of A inverse. So that's just equal to I A inverse. So what we're going to do is we're going to say, let's try and invert A, B, C, D most generally. And let's say that what we have here is we're trying to get this to equal the identity matrix. So let's suppose that A is not equal to 0. Otherwise, you swap things around because otherwise things stop to make sense. You'd swap things around, and if both A and C were 0, then the matrix would be singular. So an inverse wouldn't exist. So what we're going to do is we're going to make this 0. And in order to make this 0, we need to subtract the multiple C divided by A of this. So we're going to get D minus B times C divided by A. Here we're going to get the multiple minus C divided by A of 1. And here we're just going to have 1. Now I'm going to pretty this up by multiplying everything here by A. So I get 0, then I get A D minus BC, so that's the discriminant, so that's good. And then I get minus C and then A. So that's looking pretty good when we know what the formula is. Then I'm going to make B B0. So I get A, and then I get 0 here. And then what I get here is I get 1 minus, well, so what multiple did I take? I took B divided by the discriminant multiple. And what I'm going to do is I'm subtracting this, except I have minus C here. So I'm going to do plus C. And then here I get minus A times B divided by the discriminants. And then here I get well, let's see, by the way, just what this expression is equal to. If you have 1 plus BC divided by AD minus BC, that's equal to AD minus BC plus BC divided by AD minus BC. And so that's equal to AD divided by AD minus BC. And so what I'm going to do is I'm going to multiply all of this by 1 over a. So I'm going to get 1, 0. Then here I'm going to divide by a. So I'm going to get d divided by, and then I'll write the discriminant as delta. Here I divide by a, so I get minus b divided by delta. And then here I get 0, and here I'm going to divide by the discriminant 1, then minus c divided by delta, and a divided by delta. So that tells me that A inverse is exactly 1 over the discriminant AD minus BC times D negative B negative C A. So there, we have, I think I justified it last class as well, but here's our second justification for the formula of inverting a 2x2 matrix. So in general, row reduction lets you invert any invertible matrices. So I've in particular also taught you how to invert 3x3 matrices by doing this. Now, the thing is that I mentioned before that sometimes linear systems have solutions even if the matrix is singular. So solving singular systems. And so I'm going to write this as an instance of a row reduction problem. So example 1 is suppose that you've done some row reduction and you've gotten to the case 1, 2, 0, 1, 0, 3, 1, negative 2, 0, 0, 0, 1, and then all zeros at the bottom. And suppose you have that, and then you have the column vector 1, 2, 1, 2. Well, then what does this say? What this says that so suppose that we're solving for a times, and let's call it x, y, z, w is equal to 1, 2, 1, 2. Then this says that x plus 2y plus w is equal to 1. That's 3y plus z minus 2w is equal to 2. That's w is equal to 1. And what does the last equation tell us?
W equals 1. Yeah.
So what does it say?
That doesn't make sense.
Well, what doesn't make sense? What equation?
Because it's saying like 0 times x plus 0 times y plus 0 times z plus 0 times w equals to 2.
So that says that 0 equals 2, and that's bad. So the point is, if you have a system like this, it's clear that this has no solutions, right? So basically, we'd start off with a system that didn't look like this, right? We'd start off with some complex system. And then after reducing it to this form, you see that you have the equation 0 equals 2 that's implied by the other equations. And so this has no solutions. On the other hand, suppose that we had basically the exact same system, except instead of having a 2 here, we had a 0 here. Then what that tells us is the same stuff, except for the fact that the last equation is sensible now. It says 0 equals 0, right? So basically, I know what W has to be, right? And then I have 3 unknowns and 2 equations, right? So in general, I have an extra degree of freedom that I can use. So W is 1. So we get as a consequence that x plus 2y plus 1 is equal to 1. That's 3y plus z minus 2 is equal to 2. And then we can rearrange this to say that x plus 2y is equal to 0, and that's 3y plus z is equal to 4. And now let's say, let's x equal alpha. Then y is equal to minus alpha divided by 2, right? And 3y plus z is equal to 4, which tells us that z is equal to 4 minus 3 times minus alpha divided by 2, right? So that's 4 plus 3 halves alpha. Thus, so alpha is going to be a free parameter. The solutions are so x is equal to alpha. Y is equal to minus alpha over 2. Z is equal to 4 plus 3 halves alpha. And W, what was W equal to? Well, W was equal to 1, right? Now I can take this and I can rewrite it slightly cleverly. What I'm going to do is I'm going to take all of the terms that don't have alpha. And so what that gives me is 0, 0, 4. You know what? I made a mistake. Did I make a mistake? This is minus 2. So this becomes 4. No, I made a mistake when in my notes. This is correct. 4, 1 plus alpha times the vector 1 minus 1 half, 3 halves 1, right? Now, what does this remind you of?
A line?
Yes, but we also saw some related phenomenon when we were solving differential equations, right?
Oh, like for the solution in the homogeneous.
Yes, so this is a particular solution. And this is a solution to the homogeneous equation. So actually, I shouldn't have written that. I should have asked you, what is A applied to this matrix? Well, if this A applied to this matrix is always equal to a certain vector, no matter what alpha is, then alpha equals 0 tells us that it's something, and then alpha equals 1 tells us that it's a different thing. So it's better be that A applied to this is equal to 0, right? So what happens is you have a particular solution to the equation, and then you have a solution to the homogeneous equation. And the particular solution isn't well defined, because we could take this and we could add a multiple of it to the particular solution. It would still be a particular solution, right? So how did that come about? Well, we made the choice basically alpha equals 1 here. If we made a different choice, if we said that, for example, y equals alpha, and then we rewrote everything in terms of that, we get a different vector here. But all of those vectors would differ by a multiple of this vector. And then ax equals 0 in linear algebra speak. This says that x is in the kernel of A. And the kernel of A is just all vectors that get sent to 0. Now, the kernel of A is going to be a subspace. In particular, it's going to contain the 0 vector, right? The 0 vector gets sent to the 0 vector by any matrix. And then if you have two vectors that are sent to 0, so if you have ax equals 0 and ay equals 0, well, how matrix multiplication works is that ax plus, let's say, lambda y is the same as ax plus lambda ay, and that's equal to 0. This is the 0 vector, I should specify, plus lambda times 0, which is 0. So the kernel will always look like, let's say, C times V1 plus, let's say, C1 plus C1 times VK for some vectors, V1 through VK in the kernel. And then if K equals 0, the kernel of A is just the sets of the 0 vector. So the 0 vector is always at the kernel. The empty sum is considered 0. The empty product is considered 1. Those are conventions in mathematics. Now, what happens if you have a non-singular matrix, a matrix that's invertible? Can that have a kernel?
Mm,
And by have a kernel, I
no.
mean have a non-zero kernel. You said no? Well, okay, let's see. Let's suppose that ax is equal to 0, right? And suppose that A inverse exists. Then we have that x is equal to A inverse times 0, right? And the 0 vector, applying a matrix to the 0 vector always gives you 0. So if A is invertible, the kernel is always empty. So it's only when A is not invertible that you'll get more than one solution. And so then finding that solution, it can't be done by inversion because there isn't an inverse. And so instead you have to row reduce. And then when you're row reducing, you may either find that you're in this case, in which case it's impossible because you said that some definite number equals some other definite number and they're not equal. Or this happens, in which case you get multiple solutions. So this lets you solve. So I've now basically, what are we doing in this entire class? In this entire class, we're solving equations. They're differential equations, right? But they're equations nonetheless. And what did we do today? We now spoke about the matrix equation AX equals B, and we talked about how to solve that equation, right? And the cool thing is that when you have matrices, unlike numbers, that equation can have multiple solutions for fixed A and B. How can it have multiple solutions for fixed A and B? Well, what if the matrix has a kernel? And what if it's solvable in the case where it's solvable? So you can have that it's not solvable at all, or you can have that it's solvable with multiple solutions. And I mean, basically what happens is that if you have a k-dimensional vector space, and you're, let's say, mapping that to another k-dimensional vector space, then what's going to happen is that this k, or let's say it's going to get sent to a different vector space, W of dimension M. So it might not even be a square matrix. Then what's going to happen is that this k is going to get split up. So you're going to have that k is equal to alpha plus beta for natural numbers, where the image of T has dimension alpha, and the kernel of T has dimension beta. So what I'm saying is there's a theorem called the rank nullity theorem. And this says that sort of dim of V is equal to dim range T plus dim kernel of T. What do I mean by dimension? Well, remember that like when we were solving two-dimensional differential equations, we had that in general for the homogeneous case, they would be spanned by two linearly independent solutions. So you'd have two equations that were multiples of each other, such that every solution can be written as C times V U1 plus C times U2. And so what we're going to say is that, well, if you look at all things that are in the image of this, well, in general, if you're starting off with a four-dimensional vector space, you might have that the image is only three-dimensional. But that means that there has to be, the kernel has to be one-dimensional, because the sum of those two numbers has to be for the dimension that you're starting with. So if your dimension of your image is less than the dimension of the space into which you're mapping, that means that there will be some vectors for which you won't be able to solve the equation AX equals B, because the image is too small and there has to be vectors outside of it. But if you hit a vector and you sort of have a deficiency, let's say there's a kernel. If there's a kernel and you hit a vector, that means that that vector is actually hit by a general is going to be an affine subspace. It's going to be some particular thing plus as many multiples of vectors as the dimension of the kernel. And then if the kernel is zero-dimensional, then you're just going to get a unique solution for every single vector. So that's how linear algebra works. A linear algebra is not a prerequisite for this class, but I didn't assume any prerequisites. We're just familiar with what happens, for example, with linear first order and second order equations, right? We've seen that a lot. And so I'm saying that you sort of have the same situation here. And then I told you how to row reduce. You just do this process where you're allowed to scale, you're allowed to swap, and you're allowed to add multiples of one to the other. And why does this make sense? Well, if you have two equations like this, then multiplying this equation by a non-zero number, you still have the same system of equations. Add multiples of this to the other, you still have the same solutions to the system of equations, because you can just go back, right? And then swapping the equations, well, I mean, you literally have the same equations, right? And so eventually when you get down to this, what that tells you is, 1 times x is this, 1 times y is this, 1 times z is this, and then you know what x, y, and z are. Okay. Should I say something for 5 more minutes, or am I going to do a break 5 minutes earlier than usual? Let's do a break 5 minutes earlier than usual. So let's resume at 7:05. But are there any questions prior to that? Okay, cool. See you in 14 minutes or 13 minutes, as the case may be. Okay, so now we did a bunch of linear algebra review. So let's actually get back to solving differential equations. Although as it'll turn out, we'll get back to solving differential equations for 10 minutes and then go back to doing linear algebra. Briefly, let's get back to ODEs. So in general, we're going to be solving systems of linear equations, and I'm going to introduce a convention. Equations will now be in terms of time. Or rather, all of my functions will be functions of t. Because I have sort of like multiple equations in space. And I'm going to call those equations x, y, z as functions of t. So as an example, if we look at sort of the matrix, or rather, I'll just give an example. We might have something like x prime. And then I usually will not write the variable at all. But in this case, I'll write it x prime of t is equal to 4x of t plus 2y of t. And then y prime of t is equal to 3x of t minus y of t. So we'll write this. So we won't write the t parameter. We'll just write x prime is equal to 4x plus 2y, and y prime is equal to 3x minus y, where now x and y are functions of time. So by the way, I actually, on the first lecture, no, it was the second lecture, or was it the first lecture when we were talking about separable equations? We had a lot of fun visualizing those equations. So if you recall, you know what? I won't do this now. I will first get to the solution of the differential equation, and then I'll show you what it looks like. So recall that if we had an equation for second order linear homogeneous equations with constant coefficients, so equations of the form ay prime prime plus by prime plus cy is equal to 0, we used an ansatz. And writing it in terms of t this time, what ansatz was that? Y is equal to e to the y. So I'll say e to the lambda t, writing it as a function of t for some lambda, right? And then we had that this would be a solution if and only if lambda was a solution of the characteristic equation, right? So we are working with linear equations as well, except they're systems of equations, right? So we will use the ansatz, or rather, I guess I'll write, we are now solving the equation, and let's write it as x vector x prime is equal to matrix A times vector x. We use the ansatz. That x is equal to what? Does anyone have a guess? So what if I put e to the lambda t here? The problem is that that's a number, right? But well, a function of t, but a scalar value function of t. I want a vector. So what am I going to do? I'm going to multiply this, or rather scale, use this to scale what? So the answer is an arbitrary vector v, where v is a vector of numbers. I.e. no t dependence. So the thing is that I basically just have the function e to the lambda t, except that's no longer a vector valued function. I need a vector valued function. So I'm just going to use that to scale some vector. So for example, if let's say v in a two-dimensional case is the vector, let's say, why am I looking at my notes? I could just pick any numbers I want. If v is 1, 2, then e to the lambda t, and then like conventionally, I'll just write a dot to indicate that I'm scaling, although that's completely unnecessary. This isn't the dot product because this isn't a vector. This is just scaling. So this is the vector e to the lambda t to e to the lambda t, right? By the way, so now I'm going to sort of get to something interesting. Let's say that this is the plane, right? And let's say that t is a function of time. So if we recall what the exponential looks like, the exponential looks like this, right? So then what does this function look like? Well, at time t equals 1, it's going to look like the vector 1, 2, right? So 1, 2. So this is at t equals 1.
T equals 0?
T equals 0, thank you. At t equals 0. Then the thing is that no matter how small a negative we make t, so it's a big negative number, it's negative a billion, then this is still going to be something that's bigger than 0, although it's going to be very small, right? So what's going to happen is that this point is never going to be reached. You can think of it as sort of t equals minus infinity. That's the limiting behavior at t equals minus infinity. The limit as t goes to minus infinity of this is 0. And so what's going to happen then is like way back in the past, it was close to here, and then it very slowly moved. And then it's just going to continue moving, right? So what this looks like as a function of time is that it's just moving here. So here, I guess, is the t greater than 0 regime. And here is the t less than 0 regime. Does that make sense? So what happens then is this is sort of an incredibly simple function behavior-wise. As a function of t, as a function in the plane, you have coordinates x and y as a function of time. it looks like this just movement along a ray, not along a full line, because it never goes on the other side of that ray, because the exponential doesn't see the negative values, it only sees that. Right, cool. So what happens if we use this ansatz? Well, with this ansatz, and the ansatz is reasonable because that's what worked for the other constant coefficient linear equations. And we are working at a constant coefficient linear equation, except it's a system. So with the ansatz, ax, well, rather x prime equals ax becomes, so if I take the function e to the lambda t times a constant vector v and I differentiate it, it's the same as differentiating it in every component. And how can I rewrite that derivative?
It's gamma e to the gamma t.
Right.
Yeah.
Times what? As a scalar.
V, yeah.
Yeah, just v, because that's just a vector of numbers. Okay, I think you've said this several times. This is a lambda, not a gamma. Let's just lambdas, right? Okay, and then the right-hand side of the equation, well, so what happens is if you have a number, then you can take it on the other side of a matrix, because matrices are linear. So a times lambda x is equal to lambda ax, because that's just scaling and they're linear. So what happens is that e to the lambda t is also just a number, as in it's not a vector. So the right-hand side becomes e to the lambda t times ax, right? Now, this is just a number, right? And in particular, it's a non-zero number, right? So what we get as a result is that we can just remove this, and we have that lambda times the vector v is equal to, well, I'm actually going to rearrange this equation. A v equals lambda v. So x is equal to e to the lambda t. V is a solution when A acts on V by scaling by a number. And in this case, V is called what? Someone has seen linear algebra before, right?
Wait, for the line with the implies, why is it a v? Shouldn't it be like
Sorry, AX, thank you. Well, sorry, X is X is V. It should be V in both cases, because X is equal to e to the lambda tv, right? So I should have had a v here. There's no x anymore. We substituted x is using our ansatz. And then this equation is a bit confusing. I just, that doesn't actually occur in here, but I was just pointing out that you can take numbers outside of matrices. So this is the right equation. Well, in this case, V is what's called an eigenvector of A, and lambda is the associated eigenvalue. And by the way, postscripts. If v equals lambda v, then lambda is uniquely defined. Provided what's. So what's a trivial way to make this equation satisfied?
Like if v was 0.
Yeah, so if v is 0, then this equation is true no matter what's, right? But if v is non-zero, because sort of you can make any equation true no matter what you write if you multiply both sides by 0. If that multiplication by 0 is something that makes sense. You might have logical equations relating mathematical structures, then you might not be able to multiply math structure by 0. But if you have like vectors or other things, you can multiply by 0. Provided that v is non-zero, then the equation sort of, if lambda v equals lambda 1 v is equal to lambda 2 v, then we get that, I guess, lambda 1 minus lambda 2 v is equal to 0. And how does scaling act? Scaling just multiplies, scales every component of the vector. So if every component becomes 0 after scaling, that implies that lambda 1 is equal to lambda 2. This, by the way, is not true in linear algebra in general, because you might be working in fields of finite characteristic. And then you might have you might have weird things happening. But provided that you're working in different characteristic, this works. Okay, so the point is, now we've introduced this notion of eigenvectors and eigenvalues. And the key thing is that we care about eigenvectors and eigenvalues because they let us solve linear systems. So the solutions are going to be, well, it's a linear system, so they're going to be linear combinations of the things that you get by solving the eigenvector equation. Okay, so now I have a matrix. How do I find the eigenvalues? Well, the equation AV is equal to lambda V. That rearranges into A minus lambda times the identity matrix applied to V is equal to 0, right? Because the identity matrix applied to any vector is just that vector. So this says that 8 times V is minus lambda times V is equal to 0, which is the same as AV equals lambda V, right? So if we're looking for non-zero solutions, because remember, for a homogeneous equation like this, the one that we started off with, AX equals 0, that's the equation that we're starting off with. Sorry, x prime equals ax. It's a homogeneous equation. 0 is always going to be a solution, right? 0 prime is equal to a times 0. We want non-zero eigenvectors. So this has a non-zero solution when a minus lambda I has a kernel. And when will this have a kernel? When does a matrix fail to be invertible?
The determinant is 0.
Yeah. Determinants of a minus lambda I is equal to 0. Now, here's the key. Suddenly, when we take the determinants of a matrix with numbers with this, we get a polynomial, and the degree of the polynomial will be the dimension of the matrix. the size of the matrix. It's an n by n matrix, you get an nth degree polynomial. And this just becomes a polynomial in lambda. So we're back to solving polynomials for finding the eigenvalues. After we find the eigenvalues, we will need to find the eigenvectors. But what's a corollary of this being an nth degree polynomial? How many eigenvalues can you have at most?
N.
Yes. So in particular, there can't be more than n eigenvalues. That's a consequence of this fact. So we can see that here. So let's go to the example that we were looking at from before. I wrote down an example here. And we are going to, well, I didn't copy part of the y, so I guess I'll just write that down. What? Yeah. Okay. No, not that. Okay. So this is the equation x prime y. Rather, let's write it as xy prime applied to that vector value thing is 4, 2, 3, minus 1 xy. And so this is our A. So we want to solve the equation A v equals lambda v. But first we need to know what lambdas we're going to use to search for solutions, right? So the lambdas that we care about are such that the determinants of A minus lambda I is equal to 0. Because unless that's 0, there won't be any non-zero things in the kernel. And we want non-zero things in the kernel so that we get interesting solutions. Okay, cool. So then that becomes the determinants, which is just written, see the bars here go inwards. Well, when I don't make them go inwards, when I would just make it, then it's a determinant. And the determinant of the matrix that I want to consider is 4 minus lambda 2, 3, negative 1 minus lambda. And so what that's equal to is that's 4 minus lambda times negative 1 minus lambda, and then minus 2 by 3. So I can rearrange this to lambda squared, then I'd have minus 4 lambda plus lambda. Okay, I'll write that out. Then I get minus 4, and then I get minus 6. So that becomes lambda squared minus 3 lambda is equal to, minus 10. Okay, well, 10 has factors 2 and 5, and the difference between 2 and 5 is 3. So that's a good indication. So how does this factor?
Lambda minus 5 times lambda minus 2.
Good.
Plus
Rather plus 2. Okay, so those are the eigenvalues. And now we want to know what the eigenvectors are, because in order to solve our ansatz, we need to know what V is. So now we can try and solve this equation once we know what lambda is. So for lambda is equal to 5. Actually, what did I do in my notes first? The first thing that I did in my notes is for lambda is minus 2. So we are now trying to solve the equation. Well, I'm going to plug in lambda minus 2 here. So it's going to be 4 plus 2, 2, 3 and minus 1 plus 2 times, this is 0, right? So this is a minus lambda I, rather a plus 2i. And so we want to find an element in the kernel of this. By the way, what do you see about this matrix?
Oh, the columns are dependent.
They're multiples of each other, right? So remember, if they were not multiples of each other, then they'd be linearly independent. Then the matrix would be non-singular. Then it would not have a non-zero kernel. But we want the case where there is a non-zero kernel. So note these are multiples of one another. By the way, the fact that they're multiples of one another will only happen in the two-dimensional case. Because in the three-dimensional case, if you have three vectors that have a dependence, that does not mean that any has to be a multiple of the other. That just means that all three vectors lie on the same plane through the origin, but they don't have to lie on the same line. This is happens in dimension 2. Only. Okay, well then if we think about this, we really only have one equation. So if, let's say, if V is the vector AB, then AV is equal to 0 says that 6A plus 2B is equal to 0, and that 3A plus 1B is equal to 0. But this is the same information. Right? So, I mean, we could do row reduction, then we just get rid of one row, right? In the two-dimensional case, we don't have to do row reduction, though. Basically, what we get is the interesting equation is 3a plus b is equal to 0. That's the only equation that we have because this one is just a multiple of that. So let's say a equal alpha, right? Then b is equal to minus 3 alpha, right? So V is equal to alpha minus 3 alpha. However, we want a particular solution. We want a particular eigenvector. So just let alpha be 1. Then V is equal to 1, negative 3. And by the way, of course, the solution is going to be any multiple of a vector, or it might be you have a two-dimensional kernel. But the point is that the kernel is always a subspace. So you can always add and scale things. So if 1, 3, negative 3 is a solution, then so is alpha, negative 3 alpha. Because we're solving the equation AV equals 0. And if we scale V, then that just goes outside. So constants like that don't matter. But anyway, we have a particular solution V equals negative 3, and that's associated with the eigenvalue lambda equals minus 2. Now we have another eigenvalue, lambda equals 5. And so what we're going to do is we're going to look at the equation A minus 5 a minus 5I. And so what we're going to get is, well, okay, so 4, negative 1, 2, 3. So 4 minus 5, negative 1 minus 5. So that's negative 1, 2, 3, negative 6. What do you notice about this matrix? Again. So in terms of the columns are what?
Dependent.
Yeah. The columns are linearly dependent, which is good because singular. So that means that it is possible to find a non-zero eigenvector, which is what we're hunting for. Okay, well then, sure. So we get the equation minus a plus 2b is equal to 0. And the other thing is just a multiple of this, so it's no new information. So sure, let's b equal alpha. Then a is equal to alpha, right? So you know what? I'm not even going to do this. I'm going to say let's b equal 1. I'm not even going to bother putting the alphas. Then a equals 2, right? That lets me solve for a certain eigenvector. I can let b be whatever I want. It's going to still let me be able to find a solution. So in that case, 2, 1 is an eigenvector. For lambda is equal to 5. So in summary, for lambda equals minus 2 got, what did I get? 1 minus 3. And for lambda equals 5, I got 2, 1. So e to the minus 2t times 1 minus 3 is a solution. But so is e to the 5t, 2 times 1, right? And so the general solution is what for the homogeneous equation?
Just multiples of those added together.
Exactly, because it's linear. So if I have that's, yeah, the equation is entirely linear everywhere, so I can do this. If one thing solves the equation, then so does any multiple of it, and you can add solutions together. Now, how are we going to write this? This isn't how we're going to write the solution. So what we're going to do is, remember, we were trying to solve for xy. And so xy is going to be, in particular, c e to the minus 2t plus 2d e to the 5t minus 3c e to the minus 2t plus d e to the 5t. But that's not how we're going to write the solution either. How we're going to write the solution is just x is equal to this and y is equal to this. Okay, now we're going to get on to the super fun thing. Okay, fun stuff time. So I upgraded from last time. You know what? Let's do this example. I actually had other examples that I was going to use. You know what the other examples might be? Okay, you know what? Okay, let's just do the other. Okay, no, let's do this. Too belated. Okay, so I'm going to do something very cool. Last time I had the ability to generate, I guess actually it requires some motivation on here. First, I'll write something down. So if we think about it, what we're saying is that x prime is equal to ax plus by, right? And y prime is equal to cx plus dy. Now, what does this say? This says that if we're located at the point x naught, y naught, then what? Then x is changing as x prime and y is changing as y prime. Then I know the rate of change of x and y. And so in particular, that gives me a distribution. So if I'm at this point, then I sort of have the vector. Let's say this is the vector whose components are, so this is the vector x prime, y prime evaluated at those particular values of x and y, right? So in particular, that gives me a direction, but it doesn't just give me a direction. It also gives me a magnitude in that direction, right? So for example, yes, so it gives me a magnitude. So that's cool as well. In particular, if I have x and y are 0, if x and y are 0, then x prime and y prime are 0. Is equal to 0, 0, I guess. Then because it's homogeneous, x prime is equal to 0 and y prime is equal to 0. So in particular, if you start at this point, then what happens as time goes on?
You would get sucked into the middle.
Well, you'd stay in the middle. You were in the middle, so you stay in the middle, right? Okay, now let's imagine that we have an eigenvector. If a v is equal to lambda v, right? Then what happens? Let's say that lambda is greater than 0, and it's a real number. Then what does that tell you? So I guess if this point right here is v, then the direction at which you'd be moving, if it's an eigenvector, would be lambda times v, right? So then you get lambda v as your the place in which you're moving, right? So if lambda is greater than 0 and you start off on this ray, then you're going to move outwards, right? And it's going to look like what we saw before. So in this case that I gave you before, in this example, when I had this as a solution, lambda was greater than 0. So at large negative values, I'm close to 0 and I move outward as time goes on, right? But what if lambda is negative? What if lambda is negative? Then it's the opposite thing. Then you're pointing in the opposite direction. So if lambda is 0, then you're actually going to be attracted to 0 as time goes on. Let's say lambda equals 0. Then on the ray, lambda, I guess, alpha times v, you move outwards. And if lambda is less than 0, then you move inwards. Hand?
So it sort of measures like if it was like if you imagine it over time, it measures like how if it's going in or it's going out. Like let's say it was a liquid.
You cut out at the end, but yeah, I heard it measures what it measures.
Like what if it was like measuring like the speed of a liquid, it would see if it was coming in or coming out.
Yeah, that's a good analogy. Now, I'm actually do not want to plot this example that we just did because it's a bit of an interesting example. Let's do a slightly less interesting example. Let's say that A is equal to, and this is going to be an easy matrix to do, 3, 1, 1, 3. So let's solve for what the eigenvalues are. If we take the determinant of A minus lambda I, then we can just write down what the polynomial is going to be. What's the polynomial going to be? Written out in factored form.
Three minus gamma squared minus 1.
Yeah. And so that becomes lambda squared. Then this becomes minus 6 lambda. And then this becomes plus 9 minus 1. So 8. And so 8 is a multiple of 4 and 2. And 4 and 2 add together to give 6. So this factors as well.
Gamma minus 4, gamma minus 2.
Yeah. Okay. Now, actually, in this example, you can see what the eigenvectors are without solving it. Can you see what the two eigenvectors are going to be? So one of them is more obvious than the other. So try like the simplest possible things and see if you get a multiple of what you started with. So 1, 0 doesn't work because you get 3, 1. 0, 1 doesn't work because you get 1, 3. And that's not a multiple of what you started with, right? But what's the next easiest thing that you can try? So what if you put 1, 1 here? 1 times this plus 1 times this, then you get 4 and 4, right? And that's a multiple of 1 and 1. 1, 1 is the eigenvector associated with the eigenvalue lambda is equal to 4, right? You can sort of see that directly because 1 times this column, because when you have a vector AB, so if you have, I guess, A, B, C, D in general, and then you take a vector alpha, beta, what this looks like is that this is alpha times AC plus beta times BD. So you're taking a certain linear combination of the columns, right? Well, yeah, if you take this linear combination of the columns 1 and 1, then you get a multiple of 1, 1, right? Now, can you see what the eigenvalue for lambda is equal to 2 is going to be? So what's the next simplest thing after 1, 1, if you've already eliminated 1, 0, and 0, 1? So if you take this and you subtract it from this, what do you get?
-2. Oh, so like 1 minus 1.
Minus 2, right? 2 minus 2 is a multiple of 1 negative 1, right? So 1 and negative 1 is going to be the eigenvalue associated with 2. Usually, you actually have to solve the system to get these eigenvalues. But in this case, you can sort of see them by inspection. So let's look at this example, 1, 3, 1, 3. So we know that we have two eigenvalues that are 1, 1, and 1, negative 1. And on the plane, those are going to be precisely the vectors this, right? And then 1, negative 1, so this. So these are going to be your two vectors. So in general, if you're anywhere along these two lines, then where you start, you're going to move outwards from the origin, right? Now, what happens if you start anywhere else? So in this case, you have two eigenvectors that point outwards, right? Lambdas are both positive. So you move outwards if you're on these rays, not inwards. So let's see what happens in this example. So I'm back to brackets, and I'm going to consider the example 3, 1, 1, 3. That's what we were just considering, right? So now what I can do is I can get a distribution, which is going to be normalized. So all of the vectors are going to be the same length when I plot this, or I can do a vector fields in which I'm going to remove the normalization. So they're actually going to be different lengths. Now notice that the vector that I'm going to plot at each point is the vector ax plus by, and then cx plus dy, right? So I'm exactly plotting the vector that you get. And so if I normalize it at every point, and I consider the distribution associated with example 1, so last time this was a small display. Well, look what I did. I made it bigger, and I made the sampling plot bigger. So this should be an impressive improvement from last time. Well, then let's look at these two lines. They're the 45-degree lines. If you're on the 45-degree lines, then you're moving outwards, right? Whereas let's look at what happens at other positions. If you start here, you're going to sort of spiral in a parabolic way like this, right? So you sort of have all of these parabolic trajectories like this. So you can imagine looking here, if you start here, it's going to look like this. Can you see my cursor? And then if you start here, it's going to move like this, right? So if you start here, you're always going to remain on this trajectory. So like this trajectory on the other side is inaccessible. That's not part of your trajectory. And now what I can do is instead of plotting it as a distribution, I'm going to plot it as a vector field. And the difference is now that the vectors are going to have a length. And that's also going to show us something. So the problem is that they're too short here to see. But if you're at 0, then you're not moving anywhere. If you're precisely at 0, if you're close to 0, you're going to move very slowly. And then you're slowly going to move quicker as you move outwards, right? And notice that the vectors here are shorter than the vectors here because the eigenvalue here is the bigger eigenvalue than the eigenvalue here, right? This has eigenvalue 4, this has eigenvalue 2. So this one is twice as long as that one. Okay, now let's do another example. And then we're going to take a break after the next example. So how about the example? Let me actually just pull it up from here. It's going to be 1331. I mean, we could consider the example that we just solved before as well. So it's sort of like this, except I switched the things around. So the determinants of A minus lambda I, well, you could just write it down. It's going to be 1 minus lambda times 1 minus lambda minus 9. So that's going to be lambda squared minus 2 lambda. And then this is minus 9. And then you get a plus 1. So that's going to be a minus 8. And that factors as, well, 8 has, minus 8 has 2 factors, minus 4 and 2. And minus 4 and 2 adds to negative 2. So lambda minus 4 times lambda plus 2. So notice in this case, what we have in this case, we had 2 eigenvectors, 2 eigenvalues, and both eigenvalues were greater than 0. So I guess if we sort of had the real number line, then this would be 0. And then you had the eigenvalues 2 and 4, right? Well, as we're going to see, something very interesting happens when the eigenvalues are actually on opposite sides of 0. So now we have minus 2 and 4, right? Now, can we solve for the eigenvectors? Well, actually, if you try 1, 1, then you get eigenvalue 4, right? And if you try 1, negative 1, then you get minus 2. So for lambda equals minus 2, it's 1, negative 1. So it's going to be the same eigenvectors. Okay, but let's see what happens when they're on opposite sides of 0, because sort of I can draw the picture of the trajectories that we had in this case. The trajectories, they looked like this. So outwards trajectories. Can everyone see that picture? And then sort of the trajectory here, this is a completely different trajectory. So if you start on the red line, you're never going to be on this green line. Whereas in this case, what happens is that for the eigenvector 1, 1, it's outwards, whereas for this one, it's inwards. And so you're going to get a very different looking set of plots here. So for 1, 1, it's outwards. I guess I'm going to draw that in red. But for 1, negative 1, it's inwards. So does anyone want to guess as to how the plot will look?
Loopy.
What do you mean by loopy exactly? So if I start here, what is it going to look like?
Like it'll curl inwards, but if you start from the other side, it'll go around a bit.
Well, so if I start here, I'm going to go here, and then what happens when I'm here?
Then you go the other way.
Yeah, outwards. So it's these things, they sort of, and by the way, if I made these inwards pointing, then it would be an attracting point. They move inwards, but then they'd slowly approach this, right? Here, they slowly and then more quickly go outwards. That's what happens if they're both outwards. But if they're inwards, then they don't accumulate or diverge from 0. Rather, you have something like this, right? So let's see if that happens. So that's 1, 3, 3, 1. So 1, 3, 3, 1 is example 4. And I'm going to first do the distribution of example 4. So yeah, look at this. If you start here, you're going to exactly do that behavior. And if you start here, you're going to do exactly that behavior, right? Can everyone see that? And then you have these lines. One is repelling and the other is attracting. And so this is what is known as a saddle point. When there's a repelling line and an attracting line, you get a saddle point. Now let's see what happens when we plot the vector field associated with this. So when we have speeds involved. Notice that when you're close to zero, you're moving very slowly. So you're going to be moving quicker, then you're going to really slow down here, and then you're going to pick up as you're going out. And then if you're here, you're moving here. And so if you're here, you're moving in this direction. If you're here, you're moving in that direction. If you're here, you're moving in this direction. And if you're here, you're moving in that direction. So we can totally like see what this is going to look like. Okay, now let's take another break. And I'm going to actually, I was going through the material a bit quicker than I prepared it, so I'm going to have to write down some more examples. But let's say we resume, let's give me a full 15 minutes, resume at 8:15. So I spent actually quite a bit of time preparing that code and those examples. So that was my treat for you today. Okay, see you in 15 minutes. Okay, let's get back. So basically the two cases that we dealt with last time were when the eigenvalues were both real numbers. And we dealt with the case that they're on the same side of zero and they're on the opposite sides of zero. So by the way, to give an example where they're both below zero, you can just take this matrix and you can multiply it by -1. Then it'll swap the eigenvalues. Then you'll just literally get the same plot except with the arrows reversed. So instead of going outwards, they're now going to go inwards, right? And then this example, they're on opposite sides of zero. So the next obvious example is what happens if the roots are complex, right? Because you might get complex solutions. So complex eigenvalues. So that's another possibility. And so in general, I can just tell you when the situations are going to happen. If we have the matrix A, B, C, D, so if that's what A is, then I can write down what's the determinants of, so do not memorize this formula, for the love of God. Just do the determinant every time. So the determinant is going to be A minus lambda times D minus lambda minus BC. And so if we expand that out, that's going to be lambda squared minus A plus D lambda plus AD minus BC. And I'll go to bracket this term, and that's the determinants of the original matrix. So using the quadratic equation, the solutions are A plus D plus or minus the square roots of A plus D squared minus 4AD minus BC divided by 2. Now, if we just briefly look at what this expression is, A plus D squared is equal to A squared plus 2AD plus D squared. And so A plus D squared minus 4AD plus 4BC. What that's equal to is A squared minus 2AD plus D squared plus 4BC. And what does the original, what do the first three terms now factor as?
A minus D squared.
Yeah, and then we have this 4BC. So I can also write this as A plus B plus or minus the square root of A minus D squared. And assuming that we're starting with real numbers, this is always going to be greater than or equal to 0. So that's a square. But then we also get plus 4BC. And this can be negative, right? So this can make the square root be the square root of a negative number. Okay, so what's the summary? Well, so there are going to be repeated roots if this is the squid, this is 0. And we haven't discussed repeated roots yet, and repeated roots are actually going to be a lot more subtle than you think. So repeated roots if A minus D squared is equal to minus 4BC, right? Now, real distinct roots, and the repeated roots are necessarily real, right? Because you're going to get the square roots of 0. So I may as well just write that down, real. The reason that you wouldn't get repeated complex roots is because we're starting with real coefficients in the first place. So distinct real roots if this expression a minus d squared is greater than minus 4bc, and then a pair of complex conjugate roots. Let's write a conjugate pair. Pair of complex roots. If a minus d squared is less than minus 4bc. And additionally, in this case, the roots will be purely imaginary. If what? So if this is the square root of a negative number, then when do we get purely imaginary roots?
When a plus b equals 0.
Yeah. Now remember, this only applies if we actually have complex roots, right? If a plus b is equal to 0, but this is the square root of a positive number, then you might get two distinct real roots as well. But if it's the square root of a negative, in this case, so I mean that it's purely imaginary if you have that. So do not memorize this, obviously. Just you take the determinant of a minus lambda I and you see what you get, right? And you solve for the roots. But I'm just showing you in general what the formula is and how you do some part of this case analysis. So let's do an example. So what happens if A is 3, -4, 4, -3? So the determinants of a minus lambda I, we can just write it down, 3 minus lambda times minus 3 minus lambda. Oh, that looks like difference of squares. And then minus the product of these, which is plus 16. So this looks like difference of squares. So this is going to be, I guess, minus 9 plus lambda squared plus 16, which is equal to lambda squared plus 7. So we're in the regime of purely complex roots. What is lambda going to equal? Sorry, let me just do this quickly first. Maybe I should have done more than 2,000 more units, but whatever.
Square root minus 7.
Yeah, so plus or minus root 7i. Right? Now, I mean, let's just do the fun stuff already. So 3, -4, 4, -3. Let's spoil ourselves as to how this will look. So 3, -4, 4, -3 is my EG6. And I'm going to do Dister. So what does that look like?
Swirly.
Yeah, spirals. Sorry, not spirals, ellipses. They're going to be ellipses. So it's purely complex. So you're going to just move in an ellipse the entire time. And by the way, you can write down a formula. An ellipse has two axes. Sort of two axes of symmetry, if it's in general not a circle, if it's an ellipse. And you can write down what those two axes of symmetry are going to be. They're related to the eigenvectors, although the eigenvectors are going to be actually different. So it's not going to be exactly the eigenvectors, but there's a way to figure out what the axes are going to be. But the key is that because it's imaginary, you're not actually going to be spiraling outwards. You're going to stay on the same ellipse the entire time. So it's just an elliptical movement, infinitely going around the same track over and over again. And if we sort of look at what the vector field is, well, if you start at 0, then as always, the x prime and y prime are going to be 0. So if you're at 0, then you're going to stay there, which means that you're moving slowly if you're around 0, right? And that's indeed what we see. At 0, this almost vanishes. And notice that you're moving quicker here than you're moving here. Here, you're moving pretty slowly. And then you're picking up again, and then you're slowing down, and then you're picking up again, and then you're slowing down. That's because the stuff. Yeah.
A little like Kepler's law, because since it's farther from the center, it goes slower.
Yes. So Kepler's law, third law, I believe, states that if you have planetary motion, what's going to happen is that you're going to sweep out equal areas in equal times. Well, what happens is if you're very far away, then you have a big contribution to the area from the radius. So you're going to be moving slower than if you're nearby, in which case you can have a fat thing with a small area. So that's also a really good point. So let's see how we actually solve this system, right? So we have our, and I actually don't have this written down on paper. So I am going to just, I might make mistakes. People check my math. So if we plug this in with, let's look at lambda is equal to 7i. So we can consider, and then we're going to solve this over the complex numbers. So 3 minus root 7i, then 4, then minus 4, and then minus 3 minus root 7i. Now, do you know what's not obvious from first sight? That these two rows are multiples of one another. But that's how complex multiplication works. In fact, these rows are multiples of one another. So we can sort of see that. So let's just check that they're multiples of one another. If you sort of take a 4 and, okay, so let's multiply this row by what we get to get this row. So let's multiply by 3 minus root 7i at the top. And let's divide by 4 at the bottom, right? So if we multiply this by 4, we get 3 minus root 7i. But what happens if we multiply it by minus 3 minus root 7i? Well, these sort of aren't complex conjugates of each other. They're sort of real conjugates of each other, but you still get a pretty nice factorization. So what happens is that, well, there are going to be no cross terms. This is going to be a real number because these two things cancel out. Well, or another way to put it is that this is -1 times the complex conjugate of that. That's actually a better way to put it. You know what? I'll just write it separately. This is 3 minus root 7i, and then minus 3 plus root 7i. So now they're complex conjugates. And so that's going to be minus, and then you're going to get 3 squared, and it's sort of a sum of squares factorization. So plus 7 squared. 7 by 7 is 49. So we get 9 plus 49. And 9 plus 9 is 18. So we're going to get minus 58. That does not look promising. I want to get -4. 58 divided by 4 is not -4. That is quite a bit bigger than -4. Let's check what I did. So I'm pretty sure that it's √7. So if we do this, we get -9, and then we indeed get a +16 here. So it is plus or minus 7i. So am I multiplying by the right thing? So I want to divide by 4, and then I want to multiply by 3 plus √7i. And then I'm taking this and I'm scaling it in that way.
I think we don't get 7 squared, we get 7.
Thank you. Good catch. Yes, it's sum of squares factorization for √7. So it's actually 7. So actually we're all good. We're all good. So 9 plus 7 is 16. So it's -16 divided by 4 is -4. Yay. Okay. Thank you for sanity checking me. So these the columns are actually multiples of one another. So over the complex numbers, now imagining this is the complex matrix operating on complex vectors, and it's complex linear now. So sort of the dimensions are all going up. So now there's sort of 4 parameters that you can do, but we want it to be complex linear. Well, anyway, so these two things are multiples of one another, complex multiples of one another. That's the takeaway. So the rows are complex multiples of one another. So really, what do we get? And now what's going to happen is that the eigenvalue, the eigenvector, it's going to be a complex eigenvector over a complex vector space. So generally, you're going to be able to scale it by any complex number. And so that sort of means it looks like there's a 2-dimensional vector space of eigenvectors, but they're sort of all complex multiples of one another. And then we're only going to really care about this sort of nicer looking one, but whatever. So we have 3 minus √7i times, let's say, z1 minus 4z2 is equal to 0. That's really the only equation that we have. And so let's z1 is equal to the complex number 1. Then what do we get? Then what happens is that z2 is equal to 3 minus √7i divided by 4 times z1. So in particular, that's just minus 3 minus √7i divided by 4. I think maybe because I don't have this example prepared, maybe I'm going to want to do something more clever. But it's not like I can reduce both of these to being real numbers. But I sort of have an extra degree of freedom because I can multiply both of these by a complex number. So we're going to see what happens. Anyway, so for lambda is equal to minus √7i, what's going to happen is we're going to consider 3 minus roots. So we plus √7i, and then minus 4. And then once again, I'm not going to check it, but these two things are multiples of one another. So really the only equation that we get is that 3 plus √7i times z1 minus 4z2 is equal to 0. And now let's just set, let's say for simplicity, it would be nice if we set Z1 to 1 again. Then Z2 is going to equal, so in this case, it works out nicely. 3 plus root 7 I divided by 4. Now, if I chose different values, then I would not have that these roots would be complex conjugates of one. Well, they're not complex conjugates of one another. So in summary, for lambda is equal to root 7I, we get 1, and then 3 minus root 7I divided by 4. And for lambda is equal to minus root 7I, we get 1, 3 plus root 7I divided by 4. Okay, so what does this tell us about the general solution, and how do we make the general solutions actually look nice? So the general solution is going to be E, so this is going to be affiliated with E, then root 7I t, and that's equal to cosine root 7 t plus I sine root 7 t. Whereas this is affiliated with E minus root 7 I t, which is cosine root 7 t minus I sine root 7 t. Okay, so yeah, I am outside of my notes, so let's see if we can make this work and figure out how to make this happen. So in general, we're going to get the solution, I guess, C plus, so for the real part here, it's 1 and 1. So C plus D cosine root 7 t, and then plus C minus D sine, I sine. So this is going to be X is equal to this, and Y is going to equal, well, it's not going to be, it's actually going to be fine. So C plus D, when I C times this plus D times this, is going to be just 3/4, because these things are complex conjugates, so they cancel out. C plus D cosine root 7 t, and then here they're going to subtract from each other. So when I subtract this from this, I get minus 2 root 7. So I can write that as minus root 7I divided by 4 C minus D I sine root 7 t. Okay, now what? So now we're going to want to solve a system of linear equations that makes this, knew I should have done more than 2000. Let's learn my lesson and make this 20. I did it by 2000 again. Well, I think that's going to be just enough to last. Okay, I did not learn my lesson. I'm probably going to try and go to space again. So C plus D and C minus D can be made to be arbitrary things, but more interestingly, we are going to want this to become real. No, we're going to want C minus D to equal 0. If C minus D is equal to 0, then we're totally happy, right? So C minus D is equal to 0. Or we don't have to make it 0. because we can make it any complex number. C minus D is equal to alpha I, right? And C plus D is going to equal, so just beta. And we can always solve for this system, right? So we can always solve this. If we're given any real alpha and beta, we can find complex C and D such that this holds. So then as a result, we can rewrite this as X is equal to, well, you know what? Let's swap the names. Let's call this beta and alpha. Then we get alpha cosine root 7t. And then here, C minus D is beta I. So we get minus beta because I times I is -1 sine root 7t. And Y is equal to 3/4 alpha cosine root 7t. And then this is going to be beta I, so the I squared is -1, but that cancels with this one. So plus root 7 over 4. Wait a second. When I added these together, oh, but they were multiplied by C and D. So there was no cancellation. Wait, did I do this wrong? So what we're going to get is for the I sign, it's C and D. And then this is going to be no, I made a mistake. So this is going to be 3. Wait. Wait. If I multiply this by okay, right. Okay, I see. Let's scroll back a bunch. Yeah, so after the break, this material was not in my notes. So like I spent like 5 hours today working on the material in the first half of the lecture. So learning this stuff actually takes a bunch of time. So this is why you actually need to spend a lot of time preparing. And the 5 hours is not enough to do 3 hours of lecture. So what's going to happen here is that we're going to have C this C times this times e to the root 7it, right? So what that is going to look like is it's going to be, so if we take this cosine root 7t plus I sine root 7t, and we multiply it by 3 minus root 7i. Over 4 times C plus D times cosine root 7t minus I sine. By 3 now plus root 7i over 4. So that's the expression that we get. Let's see how this simplifies. So we're going to get C, and then we're going to get real part 3 cosine root 7t. Then this is -7. So plus root 7, because the 2 negative ones cancel out, sine root 7t. And then we're going to get the purely imaginary part plus I, and it's the cross term. So root minus root 7 cosine root 7 t. And then the other cross term is 3, and the I is already outside, sine root 7t. And then I can write plus d. And then the difference here is that the sine is the sine and this root 7 got conjugated. So both the sine and the root 7 change. So if I have sine and root 7, then it doesn't change. And next time I'll tell you what the general recipe is. But let's work out this example rotely this time. Then what's going to happen with the complex thing is that both the root 7 changes by sign, and the sine also changes by a sign. So here, all of this is going to change by a sign. Now -3. So that closes that closes the parenthesis, that closes the paren on the D. And so what we're going to get as a result is that the real part is going to be C plus D.
The 4 doesn't matter, right?
What 4? Oh, yes, there is a 4. Yeah, so 1/4. To be more correct, we should have the 1/4 everywhere. So in order for these to actually be equalities, we need the 1/4. Thank you. Although they can get absorbed into the constants, although that's sort of bad practice. So 3 cos root 7t plus root 7 sine root 7t. And then what happens here is that this changes by a sign. So it's going to be 1/4 C minus D. And then we're going to get, if so, this expression, minus root 7. This is I. Okay, fine. So this is what y is equal to. So what we are going to try and do is we're going to try and set C minus D to be purely complex, so that it cancels out with this I and makes it real. So C minus D is going to be I times beta, right? And then what's going to happen to C plus D is that it's fine if that's any real number, right? because C minus D we have here, it's going to cancel with the I purely, and C minus D is going to cancel with the I purely. So if it's I beta, then we get a real thing in both X and Y. And I'm 90% sure that the only reason this worked out is because I made these two things be complex conjugates. But there's probably a result that the complex conjugate of this eigenvector is that eigenvector, but I'm not going to immediately say that right now. Actually, maybe that's obvious. Is it obvious? Maybe it's obvious. It's sort of probably obvious. But okay, well, we're going, that's the next order of business. We're going to check that the eigenvectors are actually complex conjugates of one another. So that's going to be my claim. And this is going to be alpha. So under these conditions, then X is equal to, so alpha cos root 7t, and then it would be, I guess, you know what, let's make it minus I beta just to get rid of the, so that it actually cancels completely. Then X is equal to cos root 7t sine root 7t with alpha and beta as the coefficients. And what would Y equal? So now it's going to be more subtle. So this is going to be, you know what, let's make 1/4. Actually, no, the 1/4 does matter. Because we can't absorb it into the constants because that it would be here. So the 1/4 actually 100% genuinely does matter. So then we get 1/4 alpha. And then let's combine the cosines and the sines together. So this is going to be 1/4 3 times alpha. And then for this term, it's minus root 7 beta times cosine root 7t. And then plus 1/4. And then let's see what happens with the sine. So this is alpha root 7 sine. And then what's with the beta? So this becomes a beta 3 sine. 3 beta sine of root 7t. Okay, there we go. And these are any linear combinations of two solutions. So we could also factor it in terms, I chose to factor it in terms of sine and cosine instead of alpha and beta, but we could have also factored it in terms of alpha and beta. So you know what, that was a lot less trivial of a calculation that I expected. But I'm just going to guess what the main punchline is, and that's probably that if we solve the eigenvector for one of these, then for the complex conjugate, it's going to be the conjugate eigenvector. So this is going to be the case of purely complex eigenvectors. So let's see what that happens. Actually, in general, suppose, let's do this for complex conjugate pairs. So suppose lambda is equal to alpha plus or minus I beta. And what we have is that if we take A minus, let's say lambda 1 is plus and lambda 2 is, let's say lambda is plus, lambda 1 is plus, lambda 2 is alpha minus I beta. So suppose A minus lambda 1 I v is equal to 0. So suppose we found a thing in the kernel. Then what happens if we conjugate everything? If we conjugate everything, A remains A, right? Then lambda 1, when you conjugate that, conjugation distributes over multiplication. So it's going to be lambda 1 conjugate, which is going to be lambda 2 I v conjugate is equal to 0. So in general, if you get the an eigenvector for lambda 1, then the conjugate is an eigenvector for lambda 1 conjugate is equal to lambda 2. And so when you choose that eigenvector strategically, you'll be able to do what I did here, which is going to get you to a final result. So we finally were able to solve this system in real terms. And there's probably a bit of a shortcut on how to do this, and I'll tell you the shortcut next time. But whoops. But we did like a pretty brute force solution, and also we sort of guessed this, and then it works out. Yeah.
You could sort of see the ellipse because if you add like multiples of sines and cosines in the parameterization, you'll always get an ellipse.
Yes, except for the fact that that's what happens if it's purely complex. But if it's not purely complex, so I'm just going to do an example. Although this example isn't going to be so obvious. So I think that in example 7 in complex roots, it's going to be an example in which it's not a purely complex solution. And let's do the dister. And then what's going to happen is that the ellipse is going to actually be a spiral. Now you sort of can't see that perfectly from here, but you can sort of see that let me just show you from the U of T notes that I'm basically doing everything from. I'm not going to send you these notes. These are private and you should not be looking at them. So that example that we saw before, it's exactly a spiral. And actually you can tell the direction that the spiral is going to be from the sign of the C coefficient. So from one of the coefficients, you can tell the direction of the spiral, assuming that it's all real. On the other hand, if you have a system like the second system that we considered, if a plus d is greater than 0, and a plus d is going to be that real part. So if the real part is greater than 0, then it's actually going to spiral outwards because there's going to be an exponential factor with time that's added on. And so these notes actually don't show you how to solve the solutions. But I think the other notes that I'm using from the previous course. So actually, I can tell you a really good resource. If you go to the Stony Brook Math website and you click on this course, then it was offered most recently in last fall, I think. Or no, last spring. So a semester ago by Kevin Sacco. I TA'd for him in the fall. And he has really good notes on this for every single lecture. And so I just discovered those notes more recently and I'm going to use them. So this is an example of it spiraling inwards. So this would be if a plus d is less than 0, then it would spiral inwards. And I guess that's what we have for today. And I'll tell you a more general, well, I mean, the method that I described of choosing a complex conjugate eigenvector and then it should work out, I believe is fully general. I just made that up on the spot, of course. But there's probably a tiny bit of a shortcut to not do that much of an algebra slog, but it works out in the end. Okay, so that's the lecture for today. I am going to stop the recording.